Question 33. Find the unique solution of y double dash is equal to 1, satisfying y of 0 equal to 1 and y dash 0 equal to 2. So we need to form a solution to this differential equation. Right, given, I'll write down the given things. Y double dash equal to 1. Let this be equation 1. And y of 0 equal to 1 and y dash 0 equal to 2. These are two given values. So we can form the equation by integrating 1, we get y dash is equal to x plus c1. Let this be equation 2. Now we got our y dash. Now integrating to this is equation 4. So integrating 4, we get y equal to x square by 2 plus c1x plus c2 plus c2. So we got our y by integrating the differential equation twice. Now we can use, since the solution satisfies these initial values, we can use these initial values to eliminate these arbitrary constants. So using 2, we get y of 0 equal to 1. When we apply 0, RHS becomes 0 by 2 plus 0 plus c2. So only c2. We get c2 equal to 1. And using 3, we get y dash 0 equal to 2. So y dash 0, 0 plus c1, we get c1 equal to 2. We got c1 and c2, 6, 7. So using 6 and 7 in 5, we get y equal to x square by 2 c1x plus 2x plus 1 as our solution to the differential equation. So this is the solution to the differential equation, which satisfies the initial values. Now we need to see whether this solution is a unique solution. We can use uniqueness theorem to see whether this solution is a unique solution. Now I will just go through the uniqueness theorem once. This is our uniqueness theorem. So for a second order linear differential equation of this form, a0x y double dash plus a1x y dash plus a2x y equal to r of x, uniqueness theorem says there exists a unique solution in an interval a to b if certain conditions are met. What are those conditions? a0x in that interval a to b should be continuous, and a1x should be continuous, a2x should be continuous, r of x should be continuous in that interval. And for no values in that interval, a0x should be 0. So a0x is not equal to 0 for any x in that interval a to b. These are the conditions, and if that conditions are met, and for a there exists a y of x such that this y of x 0 is equal to c1 and y dash x 0 is equal to c2, there exists a y of x which is a unique solution to this differential equation. So this differential equation and these initial values, there exists a unique solution if this a0x, a1x, a2x, r of x is continuous in that defined interval, and for no x in that interval, that a0x should be 0. So we can use this uniqueness theorem and see whether these conditions are met. So this is our equation. We need our y double dash x. Y double dash x is equal to, I'll just create a new page here, and okay, so sorry. So our y double dash, we have y double dash equal to 1. So in our initial value, in our uniqueness theorem, we had a0x y double dash plus a1x y dash x, y dash plus a2x y equal to r of x. So comparing these two, we get a0x equal to 1, a1x equal to 0, a2x equal to 0, r of x is equal to 1. So all this, let's define an interval minus infinity to infinity, and in this interval we can see that a0x a constant, and a1 a2 r of x are all constants, and these functions are continuous in this interval, and a0x and a0x is not equal to 0 for any x element of minus infinity to infinity. So we have this condition also met. So we can say that there exists this so our y of x, our y of x, this, let me copy. So our y of x with our initial values y of 0 element of minus infinity to infinity, y of 0 is equal to, in our question it was given y of 0 equal to 1 and y dash 0 is equal to 2. Y of 0 is equal to 1 and y dash 0 equal to 2. So this satisfying this, this solution is a unique solution for our differential equation y double dash equal to 1. So by uniqueness theorem we can say this is a unique solution. So this is the solution to question number 33. We have found a unique solution satisfying these initial values.